Today, we're going to learn about exponential functions. And exponential functions are functions that take the form y equals, very much like a geometric function, y equals a times b raised to the x. Okay? So in an exponential function, whereas with a linear function, which we've been talking about, x is kind of down here. The variable that you plug in is a the variable that you plug in is an exponent, okay? And then you get out a number. So those geometric sequences that we did, those are exponential functions where we're just plugging in integer values for x. A function is, we can plug in any number for x, okay? So the difference between those geometric sequences and these exponential functions is that with these, we can plug in any number. Where with those, we're just plugging in like 1, 2, 3, 4, 5, 6. We're just plugging in the counting numbers, okay? And that would generate a sequence. This generates a series of answers as well, but it works the same way, okay? So A is, again, A is the first term, and B is, I don't know what they call B. B is like the multiplier, okay? But we're not gonna worry about what it's called. We're just gonna give you some examples. So some examples of some exponential functions are y equals 0.5 times 2 to the x. So that's a 0.5 or 1/2 times 2 to the x. And that, if I were to graph that exponential function, we're going to learn how to graph a couple. Exponential functions don't look like straight lines. They look like things that go up fast like that. Or if you have one with some exponential functions look like, instead of y, sometimes they call this f of x, right? Which implies you're plugging in for x, equals negative 2 times 0.5 to the x. And those are just examples of various exponential functions. And exponential functions look like this. This one, I believe if I graph this one, it would actually look really similar to this, because it's going the opposite direction, but it's going down this way. So I think it would look like that? It would look like this. But exponential functions could also look like this going down. So they're curvy lines that either start off slow and go up really fast, or they start off fast going down and they end up going down really slow. Okay? So they're different than linear functions, which just look like lines. And we'll talk in the next unit more about quadratic functions, which look like parabolas and stuff. Okay, so then the first thing that we do with exponential functions is we just evaluate them. Evaluate, and that just means plug in. Evaluate. F of x equals 5 to the x. So this is an exponential function as well, in which a is just 1. For x equals 2, negative 1, and 2, negative 1, and 5. Could we do that? All you do is you plug in. So f of 2 is equal to 5 to the 2. What's 5 to the 2?
25.
25. Okay? Questions about what I did? All I'm doing is I'm plugging in 2 for x up here. F of negative 1 is a little bit trickier, because that's 5 to the negative 1. Who can tell me what 5 to the negative 1 is? Remember our rules of exponents? How could I rewrite that, Sarah? It's 1/5, because this is equal to, remember, 1 over 5 to the 1, which is equal to 1/5, or 0.2. Okay? And f of 5 is some big humongous number, because that's equal to 5 to the 5th. I don't even know what that is. But if you, how much?
3,125.
3,125. Because that is 5 times 5 times 5 times 5 times 5. Right? That's what that means. So if I were to graph this exponential function, not that we're going to do that right now, okay? At negative 1, I get 0.2, right? So just, you don't have to sketch this graph, but at negative 1, I get 0.2, which is a teeny little number, right? And then at 2, I got 25, which is a big, huge number. And then at 5, I got a huge, huge number way up here. So you can see that this exponential function is doing something like whoosh, like that, going up really fast. See? Okay. Let's try another one. So for f of x equals 4 times 3 to the n, find the range. Oh, here we go with these big words again. When the domain is negative 3 and 6. Right? In other words, what they want you to do is find the y values when the x values are negative 3 and 6. And so all you're doing is you're plugging in here. But you got to be a little bit careful. Okay? So f of negative 3, that means what do I get when I plug in negative 3? It's equal to 3 to the negative 4 times 3 to the negative 3, which I could write as 4. It's kind of nice to do these by hand, just rather than plug everything into your calculator. 1 over 3 to the 3rd. Do you guys see what I did? Okay? I rewrote 3 to the negative 3 as 1 over 3 to the 3rd. Does anyone know what 3 to the 3rd is? 3 times 3 times 3. 27. Okay? So this is equal to 4 times 1 over 27. 4 27ths. Whoa, that's kind of weird. Okay? And then f of 6, well, this is going to be big. 4 times 3 to the 6. So again, if you don't know how to do this by hand, you can use your calculator. Watch. I'm going to get a graphing calculator that looks like one of those ones on the left. But if I did use my calculator, I want to use the exponent button. And usually it's a little caret thing. It depends what kind of calculator you have. But on this one, okay, I'm going to go, I would do the 3 to the 6th first. So 3 raised to, usually the caret button is raised to the 6th power, okay? And I want to do that first, which is 729, and then I want to multiply that times 4. And I get 2,916. 2,916. See it again? There it is. And so it says, find the range when the domain is 3, 6. The range is 4 over 27, comma, 2,916. So the range, remember, is just the y values when you what you get when you plug in the x value. Okay? All right. Should we try? You try? Miss Lindgren?
Sure.
Okay. You try. Whoa. You try. Equals 5. Let's just so see if you could do those. See if you could come up. We'll let one person try each one of those. See what you could come up with. Oh, I gotta pause. Pause, pause. So f of 3 is negative 54, and the way she got that is negative 2 times 3 to the 3. And that's negative 2. Remember, we do our exponents first, so 3 to the third is 27, and negative 2 times negative 27 is negative 54. Okay? Not so bad. Is that so bad? Who's got f of 0? Go ahead. Lindsay.
Negative 2.
Perfect. Negative 2. And what she did, negative 2 times 3 to the 0. Anything raised to 0 is what? 1. So that's equal to negative 2 times 1, which is negative 2. Okay? Very nice, Lindsay. And then lastly, who thinks they have f of negative 2? That one's a little bit trickier. Got that one. Go ahead, Hunter. 2/9. Perfect. It's negative 2/9. Isn't it negative 2/9? Because that's negative 2 times 3 raised to the negative 2. And so that's negative 2 times, remember that when you have a negative exponent, you bring it downstairs and you make it positive. So that's equal to negative 2 times 1 over 3 squared, which is 9. And that simplifies. You multiply the tops, negative 2 over 9. Okay? And that's how you do those. Any questions about that so far? Okay. So who gets points? I'm giving them points. Okay. Who else? Where'd you go? All right. And so next thing is you got a word problem. I'm going to type this in. I'm going to pause. You don't use a white pen because it won't show up, so you have to use a different colored pen. So the way you want to set it up is, we'll call it R of n, meaning the number of rabbits in where n, we'll figure it out, is equal to, you start with 20 times 1/2 raised to the n. Okay? So in this case, let's say you could do it like this by making a table. So here is, but in this case you have to let n equal the number of times rabbits double. Rabbits double. Okay? So if suppose 20 rabbits are taken to an island, the rabbit population, triples. So I messed up, don't write that down. Triples. So instead of this being a 1/2, this is totally wrong. This should be a 3, okay? Because you're starting with 20. When n is 1, right? After one time, it's going to be 20 times 3, or 60, right? after 2 times tripling, it's going to be 3 squared, or 180. Whoa, that's pretty big. So how many times is this population going to triple in 2 years? If it triples every half year? 4 times. Do you guys understand why it's 4 times? Because every half year it triples. The population triples every half year. So how many rabbits will there be in 2 years? Okay, there's going to be, well, it's going to triple 4 times, because it's going to triple once the first half year, then again at the end of the year, then again the next half year, then again. So this number up here is 4. So after 2 years, it's going to be 3 to the 4th. Anyone know what 3 to the 4th is? 3 times 3 times 3 times 3. I think that's 243. Is that right? What is it? 3 to the 4th? 81. Oh, it's only 81. I'm sorry. 81. So 81, and that gives you 1,682 rabbits. So that's why you see so many rabbits around. 82? Oh, 1,000. I would say it again, Justin.
1,620.
1,620 rabbits. That's a lot of rabbits. Yeah. Okay. So that's an example of real life. Here's a true story. Years ago when I was driving through Wyoming, they must have had a rabbit population problem, because it was like it was snowing. We were driving down I-80. Anyone ever go from I-80 to like Utah or something? And we were driving, and it was like a rabbit infestation. There were so many. The road was like covered in like squished rabbits. It was, and I think because I don't know what happened, but the population just went crazy. And up there's like all this free places for them to roam, and it was like gross. It was like, who's that rabbit? But luckily, a lot of places don't grow exponentially forever. Like in Louisville, when I was in college, there was hardly anyone lived here. The population of Louisville was like 10,000 or something like that. Did you know that? And now it's probably like, I don't know what, 100,000? Maybe not that, pretty close. Louisville's
like 50.
50, but so what happens is it grows exponentially really fast first, but then because there's only so many places to build houses, it kind of levels off. So what you get is actually a curve that looks more like that than exponential. All right, and then I kind of showed you how to graph. Let's just do one graph, okay? And then we'll be done. So graph. So last